Hello and welcome back to the next lecture in machine learning for core engineering disciplines, an NPTEL course. So, today what we will be doing is we will be trying to develop an understanding of logistic regression and softmax regression, which are some of the simplest classification algorithms in machine learning. So far we have looked mainly at linear regression as well as at ridge regression and lasso, and these were tools to predict a continuous variable, right. So, we were able to predict things like, let us say, the temperature in a plant, in a chemical plant, or let us say the drag that is experienced by an aeroplane or an automobile. These are all continuous variables. However, what we have not done so far is try to predict a discrete variable. So, in case you are interested in a classification problem, right, for example, you want to predict whether your product is of the desired quality or not, a material whether it has the right microstructure you need, whether it has that or not, or maybe you want to detect a fault, right, in a production line or some other problem that is occurring in an automobile, right. So, these are some binary problems. For example, in your car you have that light, right, which lights up when there is some problem. Of course, there are deterministic ways of finding out, but as ML and AI sort of increase in importance, we can envision machine learning algorithms being used to answer these kind of yes or no questions. So, that is the realm of classification, and today we will look at the simplest possible ML algorithms for these tasks. So, let us go ahead and get started with what is called logistic regression. And later in the lecture we will come to softmax regression, which is used for multi-class classification. So, logistic regression is basically a modification of linear regression. We are essentially enveloping the linear regression with a function that will allow us to answer a classification problem. So, it is a modification of linear regression used to predict the value of a binary variable. Right, and thus it is useful for binary classification problems. Okay. And like I said, there can be several examples. You may want to predict whether a material is a semiconductor or a metal, you may want to predict whether your product is of the desired quality, whether there are some contaminants in water or not, or whether the air is fit for breathing or not. These are the kinds of things that can come up from various disciplines like environmental engineering, materials, mechanical, aerospace, as well as chemical engineering, right. So, this logistic regression relies on a function which is known as the logistic function, and that is why the name is logistic regression. So, this logistic function is defined as follows: p of x equal to 1 divided by 1 plus exponent of minus x minus alpha by gamma, right. So, this is how it looks, and this is used to model the probability of the target variable being 1 as opposed to 0. Right. So, essentially, right, there are two classes. So, let us say there is class 1, we will denote that by y having the value 0, and then class 2 which means that the variable y has the value 1, right. So, what we have defined here is that this p of x is used to model the probability of the target variable taking the value 1 given a feature vector x. So, really instead of p of x we should write that we are trying to model the probability of y equal to 1 given that the feature is x, right. This is what we are really wanting to accomplish using the logistic function, right. So, the logistic function is a way to model this probability. Okay. So, let us see how this logistic function looks when we try to plot it, right. In engineering always it is nice when you have a new function, right, or maybe an old function, to plot it to see how it really looks. So, let us go ahead and do that, right. So, you have the y axis here or the vertical axis if you want to steer clear of any confusion. So, what we are plotting here is the probability of y taking the value 1 giving given x, right, and this logistic function is sometimes denoted as sigma of x, right, and on the x axis here we have x minus alpha by gamma, right. This was the argument of the logistic function. This is 0 here and this is 1 here. So, the nice thing about the logistic function is that it is always lying between 0 and 1, and when this x minus alpha by gamma, that is very low, it starts right off at 0, and then when x is equal to alpha it reaches exactly 0.5 and then continues its journey right up to 1, right. So, this value is equal to 0.5. So, in some sense x equals alpha is where the probability is half, right. So, that is one sort of way to understand what alpha is. It is the value of x at which p is half, and gamma on the other hand denotes the width of the logistic function. So, if you have a larger width there is a more gradual change from 0 to 1, and if you have a smaller width then there will be a more abrupt change from 0 to 1, right. Now, this logistic function belongs to a class of functions which are called sigmoids, right. So, a logistic function is a type of sigmoid, right. Any function that has an S shape like what I have just drawn and is mapped between 0 and 1 is called a sigmoid, and logistic function is just only one type of a sigmoid. You can cast various other functions including tan hyperbolic in this particular form, right, between 0 and 1. Okay. So, now that we know, right, how this logistic function looks, right, how do we use this to classify, right. So, typically we treat this value of 0.5, right, as sort of a threshold, right. So, anything above this, any probability above this, we will say that your class is 2, right. So, we will assign y equal to 1 your predicted value, and if your p is less than 0.5 then we will assign the class 1. Okay. So, let us write this down more formally. So, what happens is that if your p y equal to 1 given x, if this is less than 0.5, right, then we assign the class 1. So, your y hat, the predicted value of y is 0, and if p y equal to 1 given x is greater than equal to 0.5 then you will assign class 2, or in other words the predicted value of y hat is equal to 1, and this value of 0.5 here, right, in some sense it is tunable, right. So, this is called the classification threshold. and we will look at it again later, right, and I am going to denote it as P star here. Okay. So, this is what is really happening, right, and if you want to introduce the way linear regression was formulated, right, we sort of had a feature vector and then the feature vector was multiplied by a set of weights and then you had a bias, you can cast it in exactly the same form. So, instead of writing it as x minus alpha by gamma, the argument of the logistic function, which I basically did to give physical insight into alpha and gamma, instead you can write it in the more familiar form of a linear regression formulation, right. So, I will next write the probability of y equals 1 given the feature vector x as 1 over 1 plus exponential of minus beta naught plus beta transpose x. Okay. So, this is how we have always been writing the linear regression formulation, and if you try to compare it with the form using alphas and gammas, your beta naught is minus I going from 1 to p, right, the set of features or the number of features alpha I divided by gamma I, and beta is basically a vector as 1 over gamma 1, 1 over gamma 2 and so on, right, up to 1 over gamma p. Okay. So, this is how you can relate this beta naught and betas to alpha and gamma, right, or alpha I and gamma I. Alright. So, let us go ahead and see how we can train this model, right. So, to train a model, like you know, we need a loss function and we need to minimize the value of the loss function. So, what kind of a loss function is used here? Previously we have been introduced to the mean squared error, which was the loss function for a simple linear regression problem, and it also found use when we went over to ridge regression and lasso. Even there we were using the mean squared error. However, that kind of a loss function does not work here, and instead we have to use what is known as a log loss function or a binary cross entropy loss function. So, the loss function that is employed is a binary cross entropy loss function, and the engineers here would obviously appreciate this because when you have a mixing of two materials, which chemical materials, mechanical and even aerospace engineers may be familiar with, the mixing entropy is minus x log x, where x is the mole fraction, right, the amount of a certain material. So, in the same way for two classes, right, for a binary problem, this binary cross entropy loss function is defined as minus 1 over n, note the minus sign, some I going from 1 to n yi log pi hat, right. So, the probability that is predicted plus 1 minus yi log 1 minus pi hat. Okay. And here your pi hat is the probability of y equals 1 given x equals xi. Okay. So, let us see how this log loss function works. Yi is essentially the true class of the data point. Okay. And this loss function has to be minimized subject to the model parameters, which are basically beta naught and beta, and this function is typically minimized numerically. So, the model is trained by numerical optimization, and this is what was also done in a couple of lectures ago when we had discussed lasso, right, because there was no analytical solution possible, as is the case here. We had to do numerical optimization. So far we have not discussed how that optimization is done. We have just mentioned that gradient descent is one possible algorithm for us to be able to do that. Okay. So, now let us take an example and see why this log loss or cross entropy loss function really works. When you look at the mean squared error, you immediately see why it works, right. It is the difference between the predicted and the true value, and then you squared it. So if the difference between the predicted and true value is large, then obviously the loss function will be high, and your optimizer will be forced to minimize the loss function till you reach a local minimum, right, in terms of the model parameters. But here it is not entirely evident, at least at a first glance, as to why this loss function should work. So let us take a couple of examples to understand why this really works, right. So you take the example of a data point when your true class is 1 and your predicted pi hat is 0, right. So clearly in this case, right, the model is making a terrible prediction, right. The probability of the point being 1 is predicted as 0, and when the model when the value is actually really 1. So what will happen to the value, right, inside the summation, and notice the minus sign there. So I am going to denote the loss for a single point using a lowercase l, right, and this value will be minus yi log pi hat. So that is 1 log 0 plus 1 minus yi, that is 0 log 1 minus pi hat, that is 1, right. Now you know that log of 0 is actually minus infinity, right. So this is minus infinity, and then this is of course 0. So this actually tends to infinity, right. So the loss, right, when this happens is actually really high. So that is why the model tries to run away from this parameterization and will update the parameters so that the model classifies the point more accurately, right. Now the opposite scenario can also happen. So let us say your yi is 0, right. So the true class is 0, but the pi hat is 1. The model is predicting 1 as the probability of the point being 1. So in this case again the value of the loss should be very high, and that is indeed the case, right. If you write down yi log pi hat, so that is 0 log 1 plus 1 minus yi log 1 minus pi hat. So this is what you will get, and again this is minus of 0 plus minus infinity, and this tends to a very large value. So again the optimizer will have to work really hard, right. And of course I mean you can think about how this is implemented. If you try to write log 0 on a machine, obviously it may be undefined, but you can define it to be a very large number. Now the third case is when the model works really well, and in this case the loss should be 0, and we can indeed show that. So for example when yi is 0 and pi hat is also 0, then the loss becomes yi minus of yi log pi hat plus 1 minus yi log of 1 minus pi hat. So this will become 0 plus 0, that is equal to 0, right. Again you may have to define log 0 log 0 as 0 when you are implementing this numerically. And finally when your yi is equal to 1 and your pi hat is equal to 1, you can again check if you computed the log loss. In this case you will have 1 log 1 plus 0 log 0, which will again give you 0, right. So the log loss function clearly is able to capture, right, when the model is doing well and when the model is doing terribly, right. So this is how a classification model, especially logistic regression, is trained. Now we come to the aspect of how you can assess the accuracy, right, of a binary classification model. And previously again we were defining things like the R squared and the mean squared error and even the mean absolute error, which you may have come across earlier. So let us look at what happens when you want to actually assess the accuracy of this model. So the topic is assessing the accuracy of a binary classification problem. Right, or a binary classification model I should say. Okay. Now what you want is when the class is class 2, right, we will call that a positive, right, because y hat is 1 or y is 1, you want to predict y hat as also 1, right, and when your y is 0 you also want y hat to be 0. However, errors can happen in mainly two scenarios, right, and this can be a false positive which is abbreviated as FP. So in this case, right, your y is actually 0 but your y hat is 1, right. So y should have been 0, that means it should have belonged to class 1 but you are predicting it to belong to class 2. So this is a false positive and this is also called as a type 1 error, and you could instead also have a false negative Fn, and in this case your y must have been 1 but incorrectly you have said that it belongs to class 1 and not class 2. So this is a type 2 error. So our model has to steer clear of false positives and false negatives. However, it is only depending on the application you can tell how much it costs, right, to incorrectly have a false positive or to have a false negative, right. Sometimes it may not be so bad to have a false negative, in other cases it may not be bad to have a false positive. So it really depends upon your application, right. So these are the errors that can be made, and of course you can also have correct predictions, right. So these are the errors and then you can have the correct predictions, and these arise when you have the true positives Tp, and in this case y is 1 and y hat as well is 1, and you can have a true negative, right. So in this case Tn, your y, the true value is 0 and your predicted value is also 0, right. So you have done well in this case. Now these are the 4 cases that can happen: Fp, Fn, Tp and Tn, and what is done is this is arranged in the form of a matrix, right, and that particular matrix is called the confusion matrix. Right. So let us see how this confusion matrix is written down. So this confusion matrix is as follows: it is a 2 by 2 grid because like we just discussed there are 2 possibilities, right, and here you have the predicted values. Yeah, let us make this a bit big. Okay. So here you have the predicted values, and here you have the true values. Okay. So this is y hat here and this is y. Okay. Now what are the possible cases, right? Your y hat can be 1 and your y can be 1, your y hat can be 1 and y can be 0, or your y hat can be 0 and then again y can be 1 or 0. So we can now fill these 4 scenarios here, right, true positive, true negative, false positive and false negative. So when y and y hat both are 1, this is obviously a true positive. Tp. then this is a false positive. Your y hat incorrectly is 1, whereas y should have been 0. So, that is a false positive, and then the remaining 2 entries follow naturally. So, this is a false negative. Y was 1, but y hat you predicted wrongly that it is a negative, and this finally is the true negative. Both y and y hat are equal to 0. So, the desirable entries in this confusion matrix, like I said, this is called a confusion matrix. The desirable entries are the true positive and the true negatives, and the undesirable entries, they are the false positive and the false negative. So, we want to steer clear of these 2 entries in the confusion matrix. So, an ideal confusion matrix would be one in which only the diagonal entries, right, the true positive and the true negative are finite, and we would want the off diagonal entries, the false positive and the false negative, to be identically 0, right. However, in practice this does not really happen, right. So, we need to develop a more quantitative metric to assess the accuracy of a classification model. This is sort of a qualitative picture, although you have numbers, you are not able to assign metrics. So, let us see how we can assign metrics, right. So, one naive way to do it is to just look at what is called the accuracy, right. So, you can define the accuracy of the model as the number of times the model worked correctly. So, it worked correctly when you did a true positive, it also worked correctly when you had a true negative, divided by the total number of predictions that you have made, which includes the true positive, the true negative, the false positive as well as the false negative, right. So, these are the cases, but there is a problem with this accuracy metric because you are not individually looking at the true positive rate and the true negative rate. So, it could be that your data is imbalanced, right. For example, you have only 95%, almost 95% is class 1 and only 5% is class 2, right. So, classify that always predicts class 1 will seem accurate, but that is obviously not correct, right. So, we can't really look at this naive form of accuracy, right. It is not that appropriate for our problem. So, let us see what we can do instead. Okay. So, like I said, right, this simple accuracy fails in imbalanced data sets, okay. And for an example, let us say 95% of the materials you are considering are semiconductors, let us say, and then only 5% of metals. So, in this case a model that always predicts semiconductors would have high accuracy. Clearly this is a problem, right, we can't allow this, right. So, how do we fix this? We define what is known as a balanced accuracy score. So, we talk about a balanced accuracy score. Okay. So, what is this balanced accuracy? To understand the balanced accuracy, we need to define 2 more metrics. They are called the sensitivity and the specificity. right. So, let us see what these are. So, there is sensitivity, right. This is also called recall, is given as basically the true positive rate. Shortened as TPR. So, this equals the true positive divided by the true positive plus the false negatives, right. So, if you look at this expression, we are initially talking about the values that are certainly true, and then seeing also the values which should have been true, but have falsely been recorded as negative. So, if you take the ratio Tp divided by Tp plus Fn, that is when you will get the true positive rate. So, that is the sensitivity, recall or TPR, and you also need something known as specificity. So, this specificity is defined as the true negative rate right TNR, and that is equal to the number of true negatives divided by right the true negatives plus the false positives. Okay. So, now that we have defined the sensitivity and the specificity, right, we can define the balanced accuracy score. The balanced accuracy is given as the average of the sensitivity and the specificity divided by 2. Okay. So, this is TPR plus the TNR divided by 2, right, and this is very useful in imbalanced data sets. But as a matter of principle, you can use it in all data sets, right. So, that is the balanced accuracy score, right. Now, there is another manner in which the accuracy of binary classification models can be gauged, and this is called the receiver operating characteristic curve, right. So, that is basically what you do there is you change the classification threshold probability, and then you see how the model performs as you change this classification threshold probability, right. So, we will take that up in the next lecture. What we did in today's lecture was we set the foundations of logistic regression, which is used for a binary classification problem, and we discussed what is the loss function that is used, right, which is the binary cross entropy loss function. We discussed why it works, then we went from there and discussed how we can gauge the accuracy, right, or the utility of a classification model. We talked about the confusion matrix, the sensitivity, the specificity, the need for a balanced accuracy score rather than a naive accuracy score, and finally we end the lecture here. So, in the next class we will take up the receiver operator characteristic ROC curve, which is also used for a binary classification problem, and we will pivot from there into logistic regression into softmax regression, which is used for multi-class classification. Thank you, and I really look forward to seeing you next time.